Hello, everyone, and welcome to TÜBİTAK Research Institute for Fundamental Sciences. We continue our inspiring online seminar series for national and international audiences. Today, we have a very special speaker. Indeed, all our speakers are special, but our today's speaker is particularly special, and I have the honor of introducing our speaker, Isao Tanaka, professor in the Department of Material Science and Engineering of Kyoto University, director of Element Strategy Initiative for Structure Materials, and senior chief researcher at Japan Fine Ceramic Centers. We are happy to have Professor Isao Tanaka with us today. He's going to talk about data-driven discovery of new materials. The talk is part of our interdisciplinary seminar series. As usual, we will have a session for questions at the end of the talk. The question can be asked by sending a message through the chat button of the Zoom platform or just by raising hand. Professor Isao Tanaka received his Bachelor of Science degree from Kyoto University and his PhD from Osaka University. He's a very well-known, world-class scientist with broad interests in various domains of material science, such as data-centric approaches in material science, statistical thermodynamics of ceramic materials, material science of energy conversion devices, fundamental issues of structural materials, design and characterization of advanced oxides, nitrides, and related materials. In parallel to his theoretical works, Professor Isao Tanaka shows also leading-edge activities in experimental works to characterize the nano-microstructures of materials using atomic resolution electron microscopy and advanced synchrotron facilities. He is editor of 5 books and inventor of 25 patents. Professor Isao Tanaka has many awards, amongst them Honda Frontiers Award from Honda Memorial Association of Japan, Masumoto Hakaru Award from the Japan Institute of Metals and Materials, awards for academic achievements in ceramic science and technology from Ceramics Society of Japan, Philip Franz of Siebold Prize from Federal Republic of Germany, Award of World Academy of Ceramics, Dragomir Hurmezesu Award from Romanian Science Academy, Richard Fulrach Award from American Ceramic Society. With this, I want to hand over the words to Professor Isao Tanaka to begin his talk. Isao, thank you once again for joining us for this seminar, and please begin your talk.
Thank you very much for a kind introduction, and it's my great honor and pleasure to have an opportunity to give a talk here on the net, but in Turkey. And it's my pleasure. So let me start. Okay. Okay. Can you see my slide?
Yeah, it's okay. Quite nice.
Okay, I had 2 flags here. So let me start.
Thank you very much.
I'm Isao Tanaka from Kyoto. I'm talking about discovery of new material. And the word called data incentive scientific discovery is the word data intensive scientific discovery is quite popular these days. And this was a message from Jim Gray about 10 years ago. He predicted that experimental, theoretical, and computational science are all being affected by data deluge and the false paradigm of data-intensive science paradigm is emerging. And it is also true for the material science. And the data-centric material science is emerging. Probably most of you have heard about us about 3 weeks ago by a talk by Luca Gilingeri from Berlin in the similar seminar series. And he gave a very nice overview of the use of AI for the material science. And his talk is mainly from the physics viewpoint. And as a material scientist, I'm talking about material science issues for the data-intensive discovery. So where we can find material data? Traditionally, those are obtained from the experimental result, and there is a database for the crystal structures or physical properties. And quite recently, there are a lot of, or at least a few of, very well-made first principles database available for the public use. And also, there is a way to make automated experiment to collect many data. For the experimental crystal structure data, there are at least 4 major sources for the crystal structure. One is ICSD, and it contains something like 100 to 200,000 of registered inorganic crystals. For the theoretical calculation, there are few databases available, and one of the popular one is a materials project established in US. And it contains something like 130,000 of inorganic crystals. For the automated experiment, it is already quite popular in the drug discovery community. And this type of robot is routinely used for the high throughput screening. So in my talk is divided into 4 chapters, and the discovery of low thermal conductivity materials were made based on the first principles calculation done in a group. And the second one is for the daylight-driven photocatalyst. This is also done by our database on the first principles calculation. And the third and the fourth one are for the recommender system, which I will explain later what is recommender system. And we use this recommender system by the use of experimental database, in this case, ICSD or other crystal structure database. And here in the 4th chapter, we will use our own automated experimental data to search for successful processing conditions. Okay, let me start from the 1st chapter for low thermal conductivity materials. This work was mainly done by my younger colleagues. The high throughput screening has been quite popular once the DFT database is established. Once you have some physical law or expert knowledge to deduce some descriptors, and once you have a good amount of data in a library, then the strategy is very straightforward. Just go ahead to screen the library to obtain the candidate material. But things are not that easy in most of the cases. Sometimes you want to know the property which is very difficult to be computed by DFT calculation, or DFT calculation is very expensive to obtain that physical quantity. In the other case, if your search space is so huge, like millions or billions of materials, then simply DFT, exhaustive calculation by DFT is not practical. In such cases, we have to adopt another strategy, which we call virtual screening. In that case, we just obtain an initial data, which is a subset of this library. And based on this initial data, we take machine learning based on some models and some descriptors. And based on that model, we go across this library to obtain some candidates. And this candidate, because we use only a subset of this whole library, so candidate need not to be correct. So it is essential to have a validation process. And if the validation is successful, of course, it is the end of the story, but quite often validation is not successful. But still, we can use this validation data to put into the initial data and to update this model and then go across the library again to obtain candidate. So in this way, the model can be iteratively improved. I have to use laser. Iteratively improved. This process is called Bayesian optimization. And our mission here is to find out semiconductivity material of this level. Semiconductivity is quite popular quantity, and probably many of you know that diamond is quite high semiconductive material, whose semiconductivity exceeds 2,000 watt per meter Kelvin at room temperature. And the aluminum nitride is here, and the lowest semiconductivity material for popular materials is, for example, for window glass or crystalline quartz. It is just 1. So there are 3 orders of magnitude difference in semiconductivity. What we are interested in is to find out a crystalline material which has even lower semiconductivity at the level of 0.1 watt per meter Kelvin, if it exists. And so our question is whether this kind of material is existent in a known material which is registered in the material project database. At that time, it contained 55,000 crystals. And if it is existent, then the next question is which crystal shows such a low semiconductivity. By the way, quite often people use nanostructure control to decrease the semiconductivity. But what we are going to mention is intrinsic property without nanostructure manipulation or the structure control. Okay, so please remember this 0.1 watt per meter Kelvin. This is our target. But we are interested in a low semiconductivity material because we are interested in some electric materials. And this is a figure of merit for the semi-electric performance. And the semiconductivity is located here. So if you can decrease the semiconductivity, you have a chance to increase the figure of merit. So this is our motivation. We have been working on the first principles phonon calculation for a number of years. My colleague, Professor Togo, is very good at coding, and he has established this PhonoPy code, which can be used for phonon calculation and attached to the first principles engine like BAS or other first principles code. And we also established a phonon database by this PhonoPy calculation. And this code has been quite popular worldwide. We're interested in semiconductivity or semi-resistivity. And the physical origin of semi-resistivity is phonon. or phonon scattering, or phonon anharmonicity. You know that harmonic phonons do not interact. So if the crystal is only composed of harmonic phonon, you can expect to have zero thermal resistivity, which means the infinitively high thermal conductivity. But in a realistic material at finite temperature, it does not happen. Always phonon have some sort of scattering. So by the computation of phonon scattering, we can compute thermal conductivity. This is quite time-consuming calculation and very tedious calculation. But again, Togo made this code, phono 3-pi code, and we can handle 1,000 or 10,000 of first principles calculation at the same time and obtain the thermal conductivity from first principles. This is the result for the lattice thermal conductivity by this calculation. Lattice thermal conductivity is abbreviated to LTC. So this is the experimental data obtained from handbook, and this is our theoretical result at room temperature. And there are altogether something like 50 to 60 compounds shown here. And you can see that most of the data points fall on this diagonal line. And also in the data, experimental data, there are some scattering in the experimental values. So we believe that our computed value is reliable, whose accuracy are comparable to experiment. So this is really good news. But the bad news is a computational cost. As I mentioned, this is very time-consuming calculation, and we have to handle a lot of DFT results. So the computational cost is 1 day for one particular crystal using 100-core PC. So if you want to compute exhaustively all 55,000 of crystals using this PC cluster, then you need 100 years. So this is, you can find prohibitively expensive to obtain the old data. Not impossible, but is very difficult. If you have a good physical model, then the story is very simple. This is the traditional way that solid-state physicists are working on. And if you look at the advanced solid-state physics textbook, you can find this model called SRAC model. And based on SRAC model, lattice thermal conductivity is expressed by this equation with Debye temperature, Gruneisen parameter, together with atomic mass and volume per atom. We can compute by the phonon calculation these quantity from first principles. So we can compute this quantity. So let me compare this quantity with theoretical computed lattice thermal conductivity. You can find many of data points are on this line, diagonal line. It means this SRAC model is a quite good model. But at the same time, you can realize there are some outliers. We know the reason for these outliers. These outliers are located here because this SRAC model was obtained based on harmonic phonon model. And these outliers do not follow the harmonic phonon quite well. But at the same time, remember that we are interested in the low thermal conductivity material. It means we are interested in outliers, not the major crystals which obey this model. So from that viewpoint, the use of this model is not very practical, not very useful. Instead of using those physics models, we use machine learning models. And here is a library of 55,000 crystals, and we have computed only 100 of them. So it means only 0.2% of the total crystals in the library. And for the machine learning, we just make some models and some descriptors and to go through the library. Probably you are interested in which kind of descriptors, very sophisticated descriptors or not. As a matter of fact, our descriptors are very, very simple. Very simple descriptors. One is crystalline volume, and the other is crystalline density. You can find that the correlation between the volume and lattice thermal conductivity is not that good. It's very widely scattered. But with density, is almost no correlation. But we use them because they are very simple and available for all different kinds of crystals. And on top of these two quantities, we have used elemental descriptors. And as elemental descriptors, of course, there are many different kinds of choices, electronegativities or position in the periodic table, some ionic radius, and so on. But instead of using such a sophisticated quantity or heuristic quantity, we have chosen very primitive elemental descriptors, which is one hot expression of the elements. For example, lithium hydride. Hydrogen is here, lithium is here, so we gave the 1 to these descriptors. The rest of element, 34 element, there are no element included in this compound. So we gave just 0. So there are altogether 34 primitive elemental descriptors plus 2 descriptors here. So we used 36 descriptors. So here is a regression model. As I mentioned, as an input, we have 36 descriptors here, so 36 dimensions. As an output, this is observed or computed lattice thermal conductivity. We have adapted Gaussian process regression. It means we can draw a predicted curve for the lattice thermal conductivity. Together with this predicted value, we can obtain the error associated with the prediction. And this is something like 95% confidence interval. And here, inside of this exponential, this term is what we call z-score. And the z-score is shown here with a reference value, f0. If the z-score is 0, it means the probability to exceed this predicted value from the reference value is 50%. 50% is just a coin toss. Okay. It's like a coin toss. But with the increase of this z value, we can expect higher probability to exceed this reference value. Even when the predicted value is smaller than this one, still, if the error is small, then still we can expect the probability to exceed the reference value is higher than this one. In that case, z is much higher. So z-score is useful value to rank the candidate materials. So we have, so we have ranked all these 55,000 compounds in material project library according to this z-score. By the way, for the target quantity, we have taken that logarithmic of lattice conductivity with a sign minus. It means that with higher z-score, the lower predicted lattice conductivity. I'm sorry, this is a very busy picture, so let me focus only on the top 8 compounds.
Isao, you stop sharing. We don't see slide.
Oh, really?
Yeah, check.
What the problem?
Share a screen, please. Oh,
Can you
it's
see?
okay now.
So when
It's okay.
it appeared?
No, it lasts just a couple of minutes, 2 minutes.
Okay,
It's okay now.
so we made discussion process regression, and this is explanation for the z-score. And then we have focused on the top 8 compound here. And those top 8 compound shows quite high z-score. But remember that this z-score was obtained just based on the training set of just 0.2% of the total library. So this is really small subset of the total data. And also we have used very, very simple descriptors like one-hot expression of the elements. So we cannot be optimistic that this z-score, the higher z-score value correspond to the low semiconductivity material. We thought so, but in reality, we do not be so pessimistic. We were very surprised to find that after validation by first principles LTC calculation, this is quite lengthy calculation, but it is doable for 10 crystals. And we found that those of highly ranked materials shows quite low semiconductivity. Remember that our target was 0.1 watt per meter Kelvin. So those materials already showed a quite low semiconductivity. So we were very happy with those results. And also, if you are interested in the semi-electric applications, then we want to have the material with narrow band gap. But unfortunately, all these materials show quite wide band gap by DFT calculation. So those are insulators. But if you look down the whole list at the number 121 or number 144, you can find this type of compound which has reasonably low semiconductivity with quite narrow band. So in this way, using the machine learning technique and virtual screening, with the aid of first principles data set, we were able to discover this type of compound as a candidate for the semi-electrics. Okay, so within ICSD data, we were able to find several low semiconductivity materials. But of course, our universe is not much larger. We want to continue our discovery in a wider or universe in this region. And we want to know what is going on here in this universe. That is the motivation of the second part of my talk for the discovery of novel compound for the daylight-driven photocatalyst. This was done by Professor Hayashi's group. The target compound of our interest is divalent tin with some other metals. there are many different kind of mixed oxide with divalent tin. And among them, we will focus on this early transition metals because these early transition metal oxide has been widely used for photocatalysts, like TiO2. But TiO2 has a problem, it has a wide band gap, wider than the visible. And those divalent tin oxide has narrow band gaps. So it's very naive idea is by combining this type of early transition metal oxide with the divalent tin oxide, we were able to find some good visible light photocatalysts. As a matter of fact, there are 10 known oxides in this group. And among these 10, 4 of them are already reported to show high visible light photocatalytic activity. It means if you can find something new, there is a good chance to have a good photocatalytic activity. So our strategy is shown here. We again use ICSD, but we use prototype structures registered in ICSD because we are interested in novel materials, and those crystals which is already registered in ICSD is not of our interest. We just borrowed prototype structures from ICSD data, something like this type of structure or perovskite structure, spinel structure, rock salt, whatever. And in this case, cast these elements into this structure, in this case, tin into one cation site, titanium to the other atom site, or titanium to the one side and tin to the other side. And after substitution in this way, we optimize the structures and obtain the first principles energy. So altogether, the number of calculations is something like 3,400. We examined thermodynamical phase stability, which means for the compound AB with different structures, you can find this violet one is the lowest energy. It does not mean that this is thermodynamically stable, because you have to look at the whole phase diagram. And if the convex hull is drawn like this, then you can immediately find that this is not a thermodynamically stable compound anymore. It may be subjected to the phase separation to this 3 to 5, 5 to 3 compound. So we need to examine the phase stability. So it is a quite lengthy calculation, but is doable. So those all plot correspond to the each DFT calculation. And we can draw convex hull in this way to find this 215, 114 compound on the convex hull. And we have examined ICSD and found that in ICSD, there are 2 compounds existent reported, which correspond to these 2 compounds. So there is a good one-to-one correspondence between ICSD and our theoretical result. This is a good news, but at the same time, we didn't find anything new. But this is a story of tungsten oxide. If we change this tungsten to molybdenum, which is located just above the tungsten in a periodic table, then we made a similar plot and made a convex hull to find those compounds on the convex hull. And we also examined ICSD, and none of them were registered in ICSD. It means they are as yet unknown compounds. So it may suggest that there is a good chance to find those compounds, a new compound. We made similar calculation for 9 different pseudo-binary systems, and those crystals shown by red are already registered in ICSD, and shown by black are unreported in ICSD. It means there is a good chance to find those new compounds in a number of systems. But we are interested in visible light photocatalyst. So it should exceed at least the band gap of 2 eV by GGA calculation. So we can filter out those materials with narrow band gap, and we will focus on the remaining compounds. So among them, we have focused tin molybdenum oxide, and in a lab, we did experiment trying to synthesize this new compound. After some trial and error, we have succeeded to synthesize this yellowish powder. And the crystalline phase included in this synthesized sample is only a single phase. By Rietveld analysis, it is confirmed to have this crystal structure, which we found is identical to what we have predicted by theoretical calculation. And for the photocatalytic activity, we made a simple test by degradation of methylene blue under simulated daylight. So this is the degradation behavior with time. And this is a new compound, tin molybdenum oxide, in comparison with already reported tin tungsten oxide. And our new material shows almost the same or slightly better performance than already reported this tungsten oxide. So in that way, we have confirmed the presence of new compound which is suitable for photocatalytic application. So we entered this region and we found just one, but probably this is much, much wider. And we are interested in what is going on there. So that is further motivation of the third part. And the keywords in the third part is twofold. One is recommender system, and the other is chemically relevant composition, CRC. This work was done by those people. And so let me explain one by one. What is recommender system? Recommender system is quite popular. Probably most of you encounter recommender system almost every day. Whenever you buy something on e-commerce like Amazon.com or Netflix.com, they suggest something as a recommendation to let you buy, which is sometimes useful, not always. It's annoying, to be frank. But the algorithm behind that is very simple. They have huge millions or billions of customers base, and they know who bought which item. This matrix is called rating matrix. And they have an assumption that the person with similar flavor tend to buy the similar product. In the mathematical language, it is called low-rank structure of rating matrix. So based on that assumption, they have simply rearranged the element in this rating matrix and to find that this is missing element. So they recommend this customer A to buy this item 3, and the customer H to buy this item 2. We apply the same technique to discover new CRC. So let me explain what is CRC. If you look at ICSD, like in the previous tin molybdenum oxide, you can find this type of compound as an example. And they may be located on the convex hull if you perform first principles calculation or thermodynamical experiment. They correspond to chemically relevant composition, which means it is feasible to form crystalline phases, stable crystal phases. And the other composition, like these composition, which do not form crystalline structure, they are categorized as a non-CRC. So we want to distinguish CRC from non-CRC. So here is a candidate chemical space of our target. We took ionic crystal composed of 66 cations and 10 anions. For the ternary, with a simple elemental ratio with the maximum number of integer of 8, it already exceeds 1 million. For the quinary, with max 20, then it becomes 23 billion. So you can feel that it's a huge chemistry space. In comparison with that huge chemistry space of 10 billion, our knowledge in our database, experimental database, is very, very poor. In ICSD, the ternary, quaternary, quinary, the number of data is less than 10,000. You can see that there is a huge gap. Many orders of magnitude difference in between these quantities. But there are no other possibilities. We need to use these data as a training set. There are many overlaps between ICSD and other databases. And we use this ICSD as a training set. And those compounds which is registered in the other bases and not registered in ICSD, it means this pink region. We use this as a test set to validate our prediction. So obviously there is no overlap between training and test. So instead of using the rating matrix, we have chosen tensor representation of compound or of the chemical composition. Here is a cation type 66, anion type 10, and the integer set. By the way, this is for the binary, so it is composed of 100, 1,000. But this is already third-order tensor, and if we want to draw ternary system, it becomes fourth-order tensor. So it is not easy to show in an easy way. But anyway, we have chosen the tensor factorization technique, and there are many tensor factorization technique, and which are available, for example, in the scikit tensor software, open software. And we have chosen that Tucker decomposition technique. And this is a result. And this axis corresponds to the length of the core tensor. And you can see that is almost independent of the length of the core tensor. And this vertical axis corresponds to the number of correct answers included in a test set, which is ICDD or Springer material data set. The height of these birds correspond to the success rate within the top 100 composition with high predicted rating. Among this 100 composition with high predicted rating, we found that 59% or 60 are already existent in the test set. The success rate was found to be close to 60%. This is another astonishing result, because remember that we didn't use any descriptors, any of the first principle result, no prior knowledge, just to rearrange the element in the tensor to find out the discovery rate of close to 59%. The discovery rate is even 25% even for the top 3,000 compositions. It is similar for the quaternary system. But for the quinary system, the success rate is lower by 1/4. But we know the reason. Quinary system is 23 billion. So this is the number of candidates. But the number of training set is very limited. It's 1/4 or 1/5 of ternary or quaternary. So the poverty of the training set is the reason for the lower success rate. But again, from the experimentalist viewpoint, discovery rate of 15% among 23 billion is already good enough. Without this type of data, it's going to the forest without any map. So this is a good indicator for the doing experiment in a smart way. We did further validation by first principles calculation. And in the case of rubidium oxide, indium oxide pseudo-binary, this is not necessary, but for us, as first principles calculation is a kind of routine, so we can routinely examine the validity of the predicted value. And we made the first principles calculation for many different structures and found that these two compounds are located on the convex side. So by the theoretical calculation, the presence of thermodynamically stable CRC is well confirmed. Similar calculation were done for 27 different pseudo-binary systems, and the success rate was 85% within the DFT calculation. So this is quite satisfactory result, we believe. So in that way, we can make this type of map. And you can see this, the end member is changing all the time. And at certain point, you can find some red marks, which shows high probability to find new compound. So this type of information is quite useful for experimenters to do real experiment to discover something. Of course, just by DFT calculation, we are not very satisfied because it is still a pie in the sky. We really want to catch that pie and put it in my dish or in my mouth. So we, means material scientists, are responsible to actually show the predicted compound, presence of predicted compound. But for that purpose, we need how to information, how to synthesize that material, new compound. But synthesis recipe of an as yet unknown compound is not given in this type of cooking book. So we need to consult an expert if she or he is available. If they are not available, then ask an artificial intelligence for successful synthesis condition. This is the motivation for the last chapter for the use of the data by parallel experimental data set to obtain the successful processing condition by use of artificial intelligence. This was done by those people, young people. In the lab, we are not doing theoretical calculation, but we have also experimental capability. And we have established this type of parallel experiment together with parallel crystal structure identification by X-ray diffraction. And as an example, we have this pseudo-binary systems with target composition of 828. Among them, 67 are registered in ICSD, and 178 are registered in ICDD. So we use this orange part as a training set to examine whether we can successfully predict the processing condition of this ICDD compound. So for the synthesis, we have chosen 4 different synthesis methods, 23 starting material, 23 cation mixing ratios, and 5 different firing temperatures. And for the characterization, we have made X-ray diffraction. And for this particular compound, for this particular condition, we succeeded to synthesize this compound by X-ray. And for this synthesis method, we failed to obtain the target material. So we gave a score of 2 here and a score of 1 here. You can add, you can give any score as you like. You can give 100 here and 0 to them. Anyway, we will standardize and normalize this score after. We put all these score into the relating tensor. Actually, we built a 5th order tensor and made a core tensor, and by the Taka decomposition to obtain, to predict unexperimented conditions. This is a part of 5th order tensor composed of 243,000 elements. The orange means successful result, and blue means unsuccessful result in original tensor. This is just a cross-section of 5th order tensor. And there is a wide range of unexperimental conditions. This is shown as a white or blank. And there are some conditions which remain to be white. And after Taka decomposition of this original tensor, we can obtain the reconstructed tensor, which can fill this unexperimental condition. You can find some unexperimental conditions shows quite high predicted successful condition, and the rest, blue one is unsuccessfully predicted one. So let us look at test data. And those compound target compositions are not registered in ICSD, but registered in ICDD. For this target composition, which shows quite high standardized predictive scores, and by real experiment, we found the result is 100% successful. On the other hand, if the score is not that high or intermediate, the success rate by real experiment was something like 50%. So it means this standardized predictive score is quite useful to for the prediction of the successful processing conditions. So by using the parallelized experimental data and Taka decomposition technique, no DFT result, we can predict the processing conditions. So this is a summary. In the first part, I showed something about low thermal conductivity. In the second part, daylight-driven photocatalyst material. Third and fourth, I mentioned about recommender system with some ICSD data and with parallel experimental data set. Okay, this is the end of my talk. Thank you for your attention and welcome for the some comments or questions.
Well, thank you very much for this very nice and exciting talk. So now we can take short questions, please, through message or just by raising hand. Please formulate questions in a compact manner. Questions or comment, please.
Probably not so much interesting.
No, there's a question. Can you see, or shall I read this? So I can read for you.
Oh, yes.
Dear Isao, thanks for this nice, warm, and informative talk. How do you comment employing only simple description?
Okay, I can read.
Yeah.
So the question is, only simple descriptors are good in a prediction. Okay, yeah. For the descriptors, actually, we have also used more complicated descriptors. And we have evaluated the errors associated with the prediction. And it is true that by use of the more sophisticated descriptor, we can reduce the error by a factor of 2 or something. But for the ranking purpose, you don't need much accuracy. You can just rank the material. Then if it is necessary, you can, after ranking, you can make some validation. So if you need a very precise prediction, then of course, more sophisticated descriptor is useful. But for the ranking purpose, you don't need much accuracy. As I have shown that number 1 and number 3 are opposite. It doesn't matter. Anyway, it's included in a top 10 or top 30. Then it is okay. So accuracy is not that important for the ranking. And well, of course, if the prediction is for the actual value, then it's of course better to make some feature selection and use more sophisticated, physically inspired descriptors. That's true. Okay. Do I answer the question?
There's another question. Can you see?
Oh, yes. Well, the question is, In the first part, I use only 0.5%, 0.2% of the training set to predict the lattice conductivity. And I have mentioned that it is not with good accuracy. Of course, if we use much more data, 1,000 data, probably the accuracy is much better. It's similar to the use of the better descriptors for the prediction. But as I mentioned, the use of the very small data set and the very crude descriptors is still useful for the ranking. And in the other part, in the third part, I use ICSD data. And for the quinary, because the data is smaller than the ternary or quinary, that's the reason for the low discovery rate. Of course, if you have much more data, it's better. You can increase the accuracy or the success rate. But depending on the purpose, if the 15% is, if you feel not so bad, then that is the things that we can obtain by this type of approach. There may be a different way by using the more sophisticated machine learning technique to increase the success rate. So if the purpose is just to increase the success rate from 15 to 20 or 25, probably it's better to search for some much better features. But at the present moment, we have just demonstrated that even with this type of no descriptors, but just by tensor decomposition technique, 15% is not a negligible number. That I wanted to say. So it is not contradictory. It is depending on your purpose. And there are a lot of different ways to improve our result. We are just at the starting point. Am I answered the question there?
Another questions, please. Other questions, please.
Other one? Oh, other one. I cannot see. Huh? Oh, yeah, now I see. From FaithNet. The question is, do I use specific machine learning algorithm? Yes, well, we use not a machine learning technique made in a group. The first one is just simple regression model, which is available in many different kind of softwares like scikit-learn. And the tensor representation or tensor decomposition technique is available in tensor scikit-tensor. So they are available. So it's not a special technique. Everybody can do that in a simple way. And our experimental data set is available as a supplementary material attached to our chemistry material paper. And ICSD data is not a public domain, but material science data, material project data is on public domain. So you can use the data from public domain and also the software from the public domain. And you can re-examine these results by yourself. It is not so difficult. our graduate student can do that. This is very simple, not a special things. Okay, there's some other question.
Yes,
Apart
that's
from the
questions. Yeah.
from Musa, apart from the issue, machine learning will be an opportunity for the third world brain because scientific research means money. What do you think about the future in this direction? Well, this is a good point. And as I mentioned, data, well, not all data, but some of the scientific data, not from the industry, but many of the scientific data is available in the public domain. You can download them from the download side, scientific community, or some database like the Nomad in the European Union. They collect all theoretical data and experimental data. So data are available. And some of the software, most of the information techniques, information data science techniques are available in the public domain. They have that culture. So both software and data are already available. So, and for computer, you do not need the very super duper computers, just a simple PC. What we use for the this type of machine learning is just a PC or some PC clusters, less than 10 PCs, just 5 PCs. So it's not a very sophisticated hardware. So to do this type of things, it is not that expensive. Of course, you need time to think about what is the important problem, but you do not need the sophisticated equipment or sophisticated software. Of course, to do experiment or to construct some parallel experimental equipment, then probably some of the industry may have a chance to establish some robot facility to do many different kinds of experiments to perform experiment. But what we are doing is just making some simple experiment, which can be constructed in a cheap manner. Actually, we are not that rich, but we can do that. And once it is established, then this type of very small robot can do continuous experiment, even on holidays or on night, continuously there, very useful. So I think, I believe that there are many good chances for the people in the third world, and which has a good brain, but do not have the very sophisticated equipment or a lot of money to buy very sophisticated equipment. If you have a good brain, then I think it is good enough. And the internet is, of course, very important. And international collaboration and international communication is, of course, very important.
So brain is fundamental in any case.
Yeah. And of course, artificial intelligence is competing with our brain, but we have to teach artificial intelligence at the present moment. So still our brain is better than artificial intelligence at the present moment.
We have one more question from Tani Rakpai.
Yep. Is there any fallback strategy that can be used for elimination of unstable compounds? I do not understand clearly what this question means, but what we were trying to do is to find out the stable compound. So it means we are eliminating unstable compound, but well, we have to be very careful that for the definition of unstable compound. And many material scientists criticize our approach that they say that, well, you know, a case of diamond, it is not a very stable compound, but it is existing as a high pressure phase. And it is a metastable compound, and it is true that it is existing. And they are a kind of chemically relevant material or so unstable compound can be the elimination of unstable compound from my viewpoint is the same strategy to find out the stable compound, but there are some gray zone associated with the metastable compound. I don't think I answered the question in a proper way, but if my answer is not good enough, just add some question.
We can still take a couple of short questions, please. No, your answer is perfectly fine. Thank you.
Thank you.
Other questions, please. So
can we aim to discover more cost-effective way of making the material already discovered by using this method? We aim to discover cost-effective way of making the material already discovered by using this method. I do not understand clearly what the question means, but probably you think that the way using the parallel experiment is not cost-effective way. We thought that is cost-effective. Well, at least it is effective by human labor, because computer produce all data and we just analyze. So there are not much human labor expenses. But of course, the most the effective way is to use your brain or to ask your expert. And what is the best way to synthesize this material? And if he or she is very friendly and smart enough, then they can immediately tell you, okay, this is a method and this is a recipe to synthesize that material, just try. Of course, that is the best way to synthesize material. But remember that it is based on the knowledge of that expert, and he used or she used that human brain. And it is kind of intelligence of that expert. So instead of asking your next neighbor colleague, we just let the simple robot perform some experiment.
Well, if there are no more questions, perhaps we can stop here. What do you think, Isao?
Yeah, I'm fine.
So thank you once again. I hope to see you in person next year, as we have agreed before.
I'm really looking forward to visit you.
Yeah, as soon as this corona
yes.
disappears from the world.
Yeah, it's true. We are expecting an Olympic game in Tokyo next year, but I'm not sure we can have that.
Let's hope that it will happen.
Of course, we want to hope, but we cannot be optimistic. Okay, thank you.
Okay, see you.
Yeah.
See you.